For our purposes, a projectile will be an object whose motion occurs above but near the surface of the Earth. The projectile can get there by any number of means. Maybe it's a bullet fired from a gun, or a home run baseball off the bat of a major league player, or a package dropped from an airplane. The important thing is that once launched, the only acceleration of the projectile is due to Earth's gravity. This will dictate how the velocity components of the projectile evolve over time. To illustrate this, let's launch a projectile, say a tennis ball, with some initial speed v0 at some angle theta above the horizontal. When launched, the ball will follow the familiar parabolic path of projectile motion. Let's look at the velocity components of the ball at different points along its trajectory. At first, we can break the initial velocity of the ball down into its x and y components. The initial speed of the ball in the x direction will be equal to v0 cosine theta, and the initial speed of the ball in the y direction will be equal to v0 sine theta. But at some later time, the ball will be further along its trajectory, but not yet to its peak, or maximum height. The velocity of the ball at this point will be a vector that is tangent to the ball's trajectory. We again can break the ball's velocity vector down into its x and y components. Here is where we apply one of the most important characteristics of projectile motion, and that is the only acceleration of the ball is in the vertical direction, where a sub y is equal to minus g. There is no acceleration in the horizontal or x direction. Thus, a sub x is equal to 0. This means the x component of the ball's velocity doesn't change. It's constant and equal to the initial velocity in the x direction. Thus, v sub x is equal to v0 x. Now let the ball continue to move until it's at the very peak or maximum height of its path. We again draw in the ball's velocity vector, which is tangent to its trajectory, and thus at the very top it points horizontally to the right. This means the velocity of the ball is now completely in the x direction. In other words, the y component of the ball's velocity is instantaneously 0 at the peak in its trajectory. And since the x component of the velocity doesn't change, the velocity of the ball at its peak is just equal to the initial velocity in the x direction. Now the ball begins to come back down. Let's look at a position that occurs just after the peak. Here, we draw in the ball's velocity vector, which is again tangent to its path, and we can break it down into its x and y components. Notice now that its y component points in the downward direction. As before, since the x component of the velocity remains constant, v sub x is equal to v0 x. Finally, let's look at the ball's velocity right before it strikes the ground. Because of the symmetry of projectile motion, the speed of the ball at impact is exactly equal to the speed of the ball when it was launched. If we draw in the vector components, we see the y component has now increased back to its initial value, but in the opposite direction, and the x component is still its constant value of v0 x. One thing to notice from this figure is that the speed of the ball at any point along its trajectory will be equal to the magnitude of the vector sum of its x and y components. Take the highlighted position here, for example. To calculate the ball's speed, we just have to use the Pythagorean theorem. In practice, you should treat projectile motion problems just like any other problems involving motion with constant acceleration. You should draw a figure, then choose a convenient set of coordinate axes and choose your 0 locations. Note that if you always assign your positive y-axis to point upward, which we suggest you do, then the acceleration in the y direction will always be equal to minus g. Write down the variables which are known. These may include, for example, the initial position of the projectile, y initial, the final position, y final, the initial speed in the x direction, v0 x, the initial speed in the y direction, v0 y, the acceleration in the y direction, which we know is minus g, and the acceleration in the x direction, which is 0. Use the 2D kinematic equations of motion to solve for the unknown quantities. Keep in mind that the variable of time binds the two dimensions together. It's quite common to have to work in one direction first, say the y direction, in order to find time, and then use this time in the x direction to find, say, the horizontal distance covered by the projectile. Before moving on to the final section of Chapter 3, let's summarize the important points on projectile motion. 1. There is no acceleration in the x direction. Thus, a sub x equals 0, and a sub y is equal to minus g. 2. The velocity of the projectile at any point along its trajectory is equal to the vector sum of its x and y components. 3. The velocity of the projectile at the peak in its trajectory is completely horizontal and equal to v0 x. At the peak, the y component of the velocity is instantaneously 0. And 4. Over level ground, with no air resistance, projectile motion is completely symmetrical. The projectile will hit the ground with a speed equal to its initial speed at launch.